So this is where we left off last time. And so we have the GaussView software that we're going to be using next week in the lab, where you'll build several molecules. And so this is the sort of the tool window. It's a multi-window software. It's not one main window where you do everything inside that single window. You have multiple windows that pop up. And so I thought, well, here's the PowerPoint, but I've actually got GaussView open. And so we can go there. And yeah, so here's the software. And so here's the software, and then let me close out some of these other windows. Kill this, and let's make that go away in terms of its size. Okay, there, that's better. So you have the molecule, or this window where you have the different kinds of fragments that you can make. You get a periodic table. You can pick different atoms, oxygen and so on, nitrogen. Let's make ammonia. Okay, so we pick nitrogen. We have this sort of, there's different types of nitrogen. You can do a nitrogen atom. You can do a triple bonded nitrogen, any one of those kinds of things. Let's pick the sp3 nitrogen and click there. And now we've built our molecule, ammonia. Okay. There's lots of tools that you can use. You can control left click, and that zooms. You can do shift left click, and that allows you to drag the molecule around. You can rotate it around just with the left mouse button. If you use the right mouse button, you can zoom. So there's all kinds of things that you can do. The rolly wheel will also zoom, so you can play around. You can right click the window and look at some of the different viewing options. Like you can add Cartesian axes. Okay, now that doesn't look right, does it? Okay, let's zoom out. And that's because this computation hasn't taken place yet. It just stuck the molecule in there. Let's see what happens when we hit clean. Up here there's a little dust broom. Where is it? Right there, thank you. Okay. Oh dear. And Control Z works, so that's your best friend. Control Z is undo. Okay, and so let's see if we can clean that system. Well, the clean's not working. I don't know why. But after we do a calculation, then it will put the Cartesian coordinate system right on the center of mass. So let's do a quick calculation. So up here under Calculate, Gaussian calculation setup, and we get all of these options. It's really kind of hard to see. It's so tiny. We have energy, so that's one of the questions on the homework. Single point energy. So what do we mean by single point energy? Well, each structure, and we've built this structure. We have the nitrogen bonded to 3 hydrogens with certain bond lengths. That's a single point in space in terms of geometry space. And so if we just take an energy of that structure, that's a single point energy. If we come down, we have optimization. So that's going to optimize the geometry to a minimum, and it's going to optimize the angles. It's going to optimize the bond lengths, and that's all we have in this molecule: angles and bond lengths. And so if we submit, send it to Gaussian, we're going to just give it a name, ammonia. Okay. Then the Gaussian software starts. We hope. There it goes. So then this is the screen that's running and telling you what the Gaussian software is doing. It uses what's called self-consistent field. So it has the locations of the atoms. It puts the atomic orbitals on those. Then it mixes the atomic orbitals to make the molecule and calculates the energy. And it modifies those coefficients of those orbitals to make the molecular orbitals, and then calculates the energy. And so it's doing several energy calculations until the changes it makes to make the energy better don't really make the energy better. All right, so it's modifying these parameters until the energy reaches a stable energy, and that's called the self-consistent field. Okay, and so then it reaches that self-consistent field energy, and then it moves the atoms and starts over until it gets a self-consistent field for the new atom positions. And if it went up, it goes the other direction. and shrinks the atoms, or pushes them in. It makes the bond lengths longer, and if that goes up in energy, then it makes them shorter until it reaches the minimum. So we close it. Now we can open our log file in GaussView, and there we have it. Let me go ahead and put the Cartesian system on here. Yay, look at that. And the z-axis is the principal symmetry axis. Woohoo! And it's the right-handed coordinate system. See, there's x coming out of the board, just like we teach you to do. And the center of mass is in there somewhere. Okay. Now what's kind of fun about this is, let's read that geometry in again. Let's see. Open. Ammonia. And this little checkbox here says read in intermediate geometries. Okay. But did it not do it? Open. Oh, that's right. Yes, okay. So up here you've got this little window that has a 1 in it out of 4, and this only so that's what it did with the optimization, is it moved the bond lengths a little bit, didn't change the angles. For a complicated molecule, this is much more interesting, and I've got a video on YouTube where the molecule falls apart and hydrogen takes off. Like a reaction took place, a decomposition, while it was trying to optimize the geometry. And so the other cool thing is you can look at this and see all the different frames. Okay, you can turn that off, or you can let's see, where is it that we see? It's under results, optimization. This is so cool. Okay, look at this. You get the geometry optimization on the left, and over here the energies of those optimizations. And here's the gradient, so the slope with respect to those bond lengths and so on. So it's way uphill here in terms of the slope. If it moves here, it goes way downhill and way downhill and way down here. And here's the energy, so it drops. So if we cycle through our different optimizations, we get to the bottom of the energy. Now you really can't see too much happen in the last 3 energies, but if you see it cycling through the different geometries. So you can actually see the energy difference based upon the different geometries of the molecule. Okay, so that's just amazing. So then let's take this molecule, open it back up, and let's do a follow-on calculation, a frequency calculation. Submit the job to Gaussian. Okay, so now it's going through. Now it's not changing the geometry. It's going through and looking at the vibrational frequencies of the molecule. So when we talk about a frequency calculation, that was one of your questions about the job types, is the frequency calculation calculates the vibrational frequencies. Now how many would be, how many vibrational frequencies does ammonia have? Test question.
6.
How'd you calculate that? 3n minus 6, because it's nonlinear. Okay, so how many, what is n? We have 4 atoms times 3, 12 minus 6, we get to 6. So 6 vibrations. So we say, okay, then we open up that file. And then up here under results, we have vibrations. It only shows up when you load a frequency calculation, and here's our 6 vibrations. What? Check that out. Okay, and so we can click one of these and start animation. So it's a little exaggerated because it's totally inverting, so you can change the displacement a little bit. It's like it's a little too crazy. Okay. And this is a really low frequency mode, so that's, oh, let's go the other way. So that's what's happening at 1,000 wave numbers, which is related to the frequency. So it's moving slow because it's bending. And the restoring force is not much because it's just those hydrogens kind of associating with each other and repelling each other very gently. And so that's the bending mode. That's the symmetric bend, right? Because they're all moving together. Here's an asymmetric bend. Okay. Here's the other asymmetric bend. Okay. Then we get into the CH stretches, or NH stretches. How many stretches should I have? Well, I've got 3 bonds. I'm going to have 3 stretches. Just like I have 3 angles, I'm going to have 3 bends. So it's nice how it works out that way. So then let's go all the way to this is the symmetric stretch. And now this is 3,000, so it should be a lot faster. Okay, probably like that. Okay. And so that's happening up at the high end of the spectrum is the NH stretch, and the molecule's shaking. It can do both of these at the same time. It can go, right? It's stretching really fast and bending really slow. Okay. So I can't animate more than one at a time, but I can myself. And then here's the asymmetric stretch. Okay. And the other one. Okay. So these are the vibrational modes for the molecule. We've seen all 6. Okay. Isn't that cool? Think about benzene or a polymer or something like that. It just gets really complicated. And that's all of these different bends and so on are in the fingerprint region of the infrared. That's why the fingerprint region is what we call a fingerprint for the molecule. You think all of the different kinds of vibrations that can happen in that molecule, it's a pretty good diagnostic for what that molecule is. It's how that molecule is put together. And so when you take an infrared spectrum, and this is really important for forensics, because you take an infrared spectrum of a substance, you can tell very clearly if it's methamphetamine or cocaine or table salt or sugar. Okay. It's very obvious from the way the molecules bonded together. You can even do a spectral simulation here and plot those frequencies. And so you have the IR spectrum, the Raman spectrum, and we will do this by hand so that you know how that works. Okay. All right. So that's Gaussian and GaussView. It's a very short tutorial. Yes?
I know, like last year when we did the iodine lab, when I did the calculations, the bond was missing. Is there a reason for that?
Yes, okay, so in GaussView, when it draws the bonds, it kind of has a lookup table to determine whether it's a double bond, a triple bond, or a single bond, or you can have it show sort of aromatic flavor with a bond and a half. It has a dashed line. And it's just looking up its table, and its table has the typical values for drawing a bond. When we did iodine, that bond length's pretty long, and so it didn't show it as a bond. Think about that. If you had all these long associations with bonds drawn in, maybe in methane it would draw bonds between the hydrogens because the hydrogens are so close to each other. And so they have to have a cutoff value where they don't draw a line. And the iodine molecule is so long that it's beyond that cutoff value. So it doesn't show a bond between the 2 iodine atoms. So that's just a feature of GaussView that's maybe a little off. Mm-hmm. You know, maybe they should have the atom type in there and say in their lookup table, if it's a halogen bond like bromine or iodine, maybe we need to stretch that out and draw a line between the 2. Yeah. But that's a really good question because it's confusing. The GaussView is just really for displaying the molecule, and there may be some features of how it's displayed that aren't exactly correct. But if you go into the Gaussian output file, you'll actually see the bond length, and that'll be accurate, or its best estimate of the accurate bond. Yes.
How often do they update this program?
They every 6 years or so, I'd say. It's been their major update. There's more current versions. I think we're using 03. There's an 09, and there may even be a 13 now. But the features that they add are really overpowered. I mean, the features that we need haven't really changed that much since the 70s. Like the geometry optimization and the frequency calculation haven't changed substantially in decades. They're adding in other capabilities that, frankly, we would never use. Okay,
so is it like overpowered in terms of like how updated the computer has to be to run it?
No, not necessarily. We could get the more current version. And it's not that cheap, but we could get the current version, but we're not missing anything by having an older version, I guess, in terms of what we need for the class. Was your question like, why don't we have the most current version?
No, I was just
Okay.
wondering if they updated it or if it was just like, this is it.
No, they've been updating it. Let's see, the one I used in graduate school, I think we were still using, it's like Gaussian 77. And that was 92. Okay, so it was still, yeah. And so then we were really excited because we got Gaussian 93. We're like, man, we are, you know. They were adding really major features. GaussView didn't exist yet, so they didn't even have a graphical interface. All this was command line stuff, yeah. So that was very, very exciting. So this is a visual description of what Gaussian does and is doing. So we are in charge of the first step. We put in the nuclear coordinates. And so we're giving it an initial guess as to the geometry. Essentially, we're using Vesper theory because that's what GaussView does. It gets those atoms as far away as possible and makes the various shapes that we're familiar with, sp3, hybridized, or sp2, etc. And then it calculates the energy of that geometry. And then you can take the derivative of all of those energy terms and get the gradient. So essentially the slope with respect to those coordinates will give you the gradient. The gradient is just the slope in multiple dimensions. Okay, so it's sort of, where's downhill? I might have a dimension this way and a dimension this way, but it goes downhill diagonally. And so that would be just the gradient. The instantaneous slope on a multidimensional surface is the gradient. And so once it calculates the gradient, it can tell if it's at a minimum. Because if the slope is 0, you might be at a minimum. But if it's not 0, you're not at a minimum, right? Just think about a one-dimensional curve. If you're at the bottom of the hill, the slope is 0. You can get fooled and be at the top of the hill and calculate the slope and be, hey, it's 0, I'm at the bottom of the hill, but you may not be. And we'll get to that in a second. So is the gradient 0? If no, then you're not at a minimum. And so you go up and you change the geometry. Now, we don't have to do that. Gaussian does that. And so it stretches the bonds or bends them or what have you, and then recalculates the energy, recalculates the gradient, asks if it's a minimum. So it will do this for ammonia, and it did it for about 20 seconds. Okay. For larger molecules, it takes a minute or two. And then eventually it says, yes, I'm at a minimum. If I move my nuclei, my energy won't drop very much. If I move the nuclei, the forces on those nuclei, if you think about this gradient as sort of gravity pulling the molecule downhill, the forces are at a minimum as well. So there's really no substantial reason to change the geometry anymore. You never hit 0, you just get below a threshold. And it says, I'm below the threshold, so I'm good. Then we go into a second calculation, the frequency calculation. Now this takes those atom positions and essentially moves them back and forth and calculates the curvature of that energy surface. And essentially it's taking the second derivative and calculating the vibrational frequencies. Now this whole idea of negative frequencies, if you remember the harmonic oscillator plot, if the energy surface looks like this, okay, so if the energy surface looks like this, the potential energy, and this is V equals 0, let's do this, energy. This is so it's 1/2 the vibrational frequency. We typically will do that in wave numbers. So this little bit down here at the bottom is the 0 point energy, and it's 1/2 of that vibrational frequency. So if I have a CH stretch at 3,000 wave numbers, then the 0 point energy from that CH stretch is going to be 1,500 wave numbers. It's 1/2 that vibrational frequency. Write that down. Okay. So this is the vibrational frequency. In a molecule, how many 0 point energies are there? it's kind of a tricky question. There's one 0-point energy, but how many components add up to give you that number?
All of the vibrations.
All of the vibrations. So you have 3n minus 6 of these little pieces. You add all of those up to get the 0-point energy. Now, if you just have one vibration, like in an HCl molecule, a linear molecule with just one vibrational frequency, then you can calculate the 0-point energy if you have that vibrational frequency. Okay. So you just take 1/2 of that, and that's your 0-point energy. Okay, but what if you're at the top of a hill? All right, you've reached a jump. Now, how would Gaussian get stuck there? Well, it might minimize the energy with respect to several other coordinates and reach a minimum, but it's at a maximum with respect to one or more coordinates. Now, what's the vibrational frequency here? If it does this calculation, it's going to end up with a negative value. Okay, negative something. I don't know, negative number. And that would be called an imaginary frequency in the terms that Gaussian uses. Okay. And so if it has negative vibrational frequencies in the output file, then the geometry is not optimized. We're not at a minimum. And so negative frequencies, if you say yes to that, and then you actually have to do this manually. So you get the frequency calculation output, you look for negative vibrational frequencies. If you see any, then you've got to reduce symmetry. So typically you get stuck here because Gaussian says, all right, I've got a D3H molecule and I have to stay D3H. And so it's only going to find places on that D3H energy surface. And what if the molecule wants to slip, like staggered versus eclipsed ethane? Eclipsed is D3H. It would definitely get stuck in a maximum. But if you break the symmetry a little bit, then it can roll downhill and become the staggered version. So eclipsed is D3H, staggered is D3D. And so you change the symmetry, you break that symmetry a little bit, and now it's D3 and it can roll downhill and find the D3D structure. So you reduce the symmetry, which is a change in the geometry, which means you start over. Okay, do the geometry again and again and again. Then you end up with the frequency calculation. Eventually you get an output that has no negative frequencies, and then you're at the optimized geometry and you have energy data that you can use. Yeah.
Are these relative minimums or are they absolute?
We really can't know. Okay. Now in a small molecule you can. Like the staggered ethane is the global minimum. Okay. Eclipsed ethane, where the hydrogens are on top of each other, that's a local minimum but a maximum with respect to the dihedral angle.
Okay.
Now, when you've got a protein and you've got all those, the backbone angles, I forget, it's like psi and phi or whatever, but anyway, you have the angles around the sigma bonds in the amino acid backbone, and the R groups are sticking off. Okay, I don't think you would ever know if you're at the global minimum, because you can have three choices with all of those dihedral angles. And in fact, you can take a protein and you can look at a plot of one dihedral angle, like between the carbon and the nitrogen, and the other one between the carbon and the carboxylic acid group. And so that central carbon, the chiral carbon, has two dihedral angles on either side. If you plot one on the x-axis, one on the y-axis, you'll see regions where that protein is a beta sheet, a region where those dihedral angles give you an alpha helix. And then other regions where there's turns, like different kinds of turns that switch between beta sheet and alpha helix. So these dihedral angles and these local and global minima, those are really important concepts in the structure of the molecules. And so we'll just touch on that a little bit with our exercise in Gaussian, but it'll at least open the door for you to explore that more if you're more into biochemistry research. Dihedral angles are really how we get all of the structures of our proteins. That's the only difference between an alpha helix and a beta sheet, is the dihedral angles along the backbone. Now, what makes those structures stable are the R groups. So those R groups will hold them into one form or the other. So then the post-calculation options, we can simulate spectra, IR Raman, NMR, UV-Vis. We can do these electron density clouds and electrostatic potential maps. So let's work on interpreting some of these things. Okay, so these are two total electron density surfaces. The one on the left, or the one on the top here, it looks like, yeah, that one is 0.0004. Okay, so let me go ahead and write that on here so you can see it. So this one was calculated with this ISO value of 0.0004. And so this one down here is 0.05. Okay. What do those numbers mean? Well, this is a surface, and the electrons are what are holding this molecule together. Where do you think the most dense region of the electrons are? It's between the atoms, right? These are positive nuclei, and the electrons are sucked in really close to the molecule. But if I wanted to get sort of 99.96% of all the electrons in sort of an envelope, and that's a floppy looking envelope, then that's what's plotted on the upper left. So that ISO value of 0.0004 is where, if I'm standing there, that's sort of the density of the electron cloud that I feel. Like if I pick a little volume, it's got, I guess, 0.0004% chance of an electron being in that little volume. Okay. If I go closer to the molecule, it gets higher. If I go further away, it gets lower. So I can walk around the molecule and connect all the little points that have the same probability of the electron being in there, 0.0004. And that's what generates that little surface, that purple surface on the upper left. So all of these values on this surface have this ISO value. And you can think of it as the probability of the electron being in that spot. Okay. Now, if I get closer to the molecule, the probability should go up, right? And this one's 0.05. You see? So all the places on this surface have the same ISO value, the same probability of an electron being in that spot. If I go in below that surface, the probability goes up. Another way to think about it is this surface contains 1 minus that ISO value. So the top one contains 99.9%, 99.94% of the electron cloud. Do you follow me? And then this one down here contains just 95% of the electron cloud. So this is 95% of the electron cloud. Up here is 99.96% of the electron cloud. What would the surface be if I wanted 100% of the electron cloud? Infinity, all space. So we can't do that because that's not useful, you know. And so we come in a ways. 99.96 is pretty good. It has the shape of the molecule, and so we have this total electron density surface. It's a surface around the molecule that contains 99.96 or whatever value you want to pick percent of the electron cloud inside of it. Now, what if we walked along that surface with the positive charge, and we could measure the force on that positive charge? So we're standing right above an oxygen with lone pairs, and we're like, wow, this positive charge is really attracted to this spot. There must be something negative down there. And then I walk over to an acid proton, and I say, wow, this positive charge is not very attracted here. It's kind of repelled a little bit, so there must be something positive under the surface here. And so I go around mathematically, and I map out the positive and negative attractions to a positive charge, and I can put an electrostatic potential on this map, on this surface. So I can map the electrostatic potential onto the total electron density surface. And that's what an electrostatic potential map is. So this is what I just said about containing the electron cloud. Let's go here. So if we walked around the molecule with this positive charge, it would be attracted or repelled in different regions of the molecule. So this is the total electron density surface, but then the electrostatic potential has been mapped on top of it. And so up here on this benzene ring, the positive charge was attracted to the negative electron density in the pi cloud. And then over here on the sides, that positive charge was repelled by the unshielded proton on that hydrogen. So that hydrogen's electron cloud was pulled into the ring and exposed a little bit of positive charge from that hydrogen nucleus. And if I'm standing just on that surface, I can tell there's a positive nucleus nearby. And so this is an electrostatic potential map, and I'd like for you to understand how to read it or even construct one. So if you're given a molecule like let's just do one on the board really quickly. Oh, let's pick something interesting. How about methylamine? So, So I've drawn the total electron density surface, 2 dimensions, but you get the idea. Okay. And you're walking around with your little electron. I don't have a blue. But if I'm walking around this molecule on that surface, where are the positive regions? Yep, so this part right here will be positive. And these hydrogens will be positive. And so those regions would be blue on the electrostatic potential map. What about up here? If I'm walking along here with a positive charge and I get close to those lone pairs,
It's going to be pulled inwards.
yeah, so that's going to be the red region. So it's not that hard, right? Now, if this were going to react with benzene, what do you think would hit what? This lone pairs would probably go after those hydrogens. It's not going to go towards the ring. You got negative and negative. They're going to repel each other. And this is why I always thought it would be a great idea for a student to come out of Chem 2. You just learn about the shapes of molecules in Chem 1 and Chem 2 and so on, and go right into PChem and learn about molecules so that electrophilic attack actually makes sense when you get to it in organic. You know?
I feel like this would just make sense to have it taught in organic, because this would actually help.
Yeah, and so they are. You'll start to see computational chemistry show up more in organic books. Okay. As far as some of the electron density stuff, this is an interesting point. You can kind of just use the size of that electron density too to tell you something about where the electron cloud is. And I just want to show the difference between HF here. Look where the bulk of the electron density is. It's on the fluorine versus lithium hydride. So that's the hydrogen right there. And so lithium hydride is showing that the electron density is on the hydrogen, not on the lithium. And so we typically think hydrogens are always positive, but no, not when you put it with another atom that would rather be a cation. And so here, lithium has transferred electron density over to the hydrogen, and you can see that from the total electron density surface. Okay, let's do some practice. Okay, it's just the rest of the information in this PowerPoint is just kind of showing that the computational chemistry geometries are pretty good. It gets bond lengths pretty well, but the frequencies, they're just okay. You can be pretty far off on some of the frequencies. Okay. So let's do let's do a board problem though, because I've got one on the test that I'd like for you guys to have a good shot at getting. So I'd like to do something that's a little more challenging. And I think we have time. We've got 2 minutes. That's all you have on the test for this problem as well. Okay. So here's the question. And we got to go pretty quickly. A 220, let's see, lambda for a transition. So lambda equals 220 nanometers for the first overtone. So you got a vocabulary word in there. Of an electron in a box. One-dimensional box is assumed. How long is the box? This is a perfect example of why we use spectroscopy. Now we can do these problems from the ground up, start with the wave function and the box length and the electron mass and the temperature and simulate a spectrum. But in real life, what you get is a spectrum and you ask questions about the system, about the molecule. So we've got a peak that appears to be the first overtone and it's at 220 nanometers and we know it's an electron, but we don't know what's the size of the system. So let's figure out what the size of that system is. Okay. So what's our approach? First of all, we got to get out of wavelength and into transition energy, right? So we got to do that first. And then once we know the transition energy, we've got to know what transitions it is, the N to N prime, right? What's involved in the first overtone. And then once we get that, we have Planck's constant, speed of light, mass of the particle. We can put all that stuff in and solve the problem. Okay. So quickly, let's get out of wavelength and into delta E. So delta E is equal to h nu is equal to what's nu? Yeah, C over lambda, H, C over lambda, okay? And so we have lambda, we know H, we know C. So we have 6.626 times 10 to the negative 34 joules times seconds. 3 times 10 to the 8th meters per second, the speed of light. And then 220 nanometers. Now, this is where your metric system really comes in handy because nano is 10 to the minus 9. So just write that in there, 10 to the minus 9 meters. Always write this out first with the units. If you don't do the units, you're going to fail this test, or you'll fail this problem. So meters is gone, seconds is gone, we're left with joules. So everything works out. I want energy, I got energy. Okay. Why run a marathon with no shoes? Okay. Use the units. Okay, those are your shoes. All right. So the way I do this problem, now it's the practical tip. 6.626 times 3 divided by 220. It's like, wait a minute, what's going on here? And then I have times 10 to the minus 34 plus 8 minus a minus 9. Okay, plus 9. This keeps you from destroying yourself on your own calculator. Okay, I can do that without making very many mistakes. And then I can take 34, negative 34, and add 9 and add 8. Okay. In fact, let's do this little piece right here. To save time, I've got it written down. Minus 17. Okay, and this is joules. Is everybody clear to this point? Mm-hmm. Okay. So then that ends up being 9.04 times 10 to the negative 19 joules. Then we do a gut check. Is this roughly, does it look right for a visible photon. Yeah, it does. It's 10 to the 19 joules is the energy of about one visible photon. We did some of those problems earlier on, I think, in the very first homework set. So we've got our energy. Now, because of board space, and so that you can see it up there, it's a little different. No, it actually makes it worse when I turn on it. Okay. There's no way to win. Okay. Let me erase this part just so we can do the next piece. Okay, so that's delta E for the first overtone. First overtone is 1 to what? 4, exactly. Delta N is equal to plus 3. Okay. The fundamental is delta N equals plus 1, and it goes 1 to 2. So then 1 to 4. And so then this delta E is equal to 4 squared h squared over 8ml squared minus 1 squared h squared over 8ml squared. So those of you who were intimidated by this problem at the beginning, this is the piece where you would have probably had trouble, is having confidence in yourself to know how to take the definition of an overtone and turn it into this. Because once you have this, then you're done with the problem. You just have to do the math, right, or the algebra. But this is the real problem right here, is knowing that the first overtone can be turned into this. Now, if you have the transition equation written on your note card or whatever, you could have put that into the delta N equals 3 transition equation. But what is N in that case? It's the lower N. It would be 1. So I think it was 6N plus 9 or something like that. But anyway, you have 4 squared, which is 16, minus 1 squared, which is 1. So that would be 15. 15h squared over 8ml squared is equal to 9.04 times 10 to the minus 19 joules. And this is my one unknown. So I just have to solve for L. Okay. So I'm going to go do that algebraically. We'll put all the numbers in. So L is equal to the square root of 15 times 6.626 times 10 to the minus 34 joules times seconds. I got 2 of those, and I know that one of them is going to have to cancel mass, and so I'm going to break the joule out on this one. So 6.626 times 10 to the negative 34 kilograms meters squared per second. That's my second Planck's constant, because I have 2 of them up here. Now the denominator, 8, and the mass of an electron. Why don't you just, for good purposes, write down on your note card the mass of the electron, the mass of a proton, and the mass of the neutron. Look those up. Everybody hear me? Mass of the electron, mass of neutron, mass of proton. I may write them on the board too, just in case people forget. Mass of the electron is 9.1 times 10 to the negative 31 kilograms. Okay? Now, L squareds come out, I put the energy down in the bottom. So I took the energy over to the denominator and pulled L over to the right. And so then this is the energy term, 9.04 times 10 to the minus 19 joules. Okay, so let's look at our units. Joules and joules cancel. Kilograms and kilograms are gone. I have a per second up here and a second there. And I'm left with meters squared. And I've got a square root. That's fun. I like it when the squares and the square roots work out. Now let's write it out in the easy way. So L is equal to the square root of 15 times 6.626 times 6.626 over 8 over 9.1 over 9.04 times 10, and this is where it gets crazy, minus 34 again, plus 31. Remember, don't screw up that negative. It's in the denominator, so it's minus a negative. Plus 31, and then plus 19. And then we have the square root of everything. And this is meters squared. So you take just a ridiculously long calculation on a calculator, and you've reduced it to something fairly simple. Okay. Now, order of operations. Trust your calculator. Order of operations says I can do these in any order. Okay. So listen to how I type this into my calculator. Pay attention. 15 times 6.626 times 6.626 divide 8 divide 9.1 divide 9.04. Okay, you don't have to put 4 billion parentheses in this stuff. Okay, you get into the parentheses, that's how you screw simple calculations up. Okay, and then you get your result and write it down, and then you do your powers of 10. Okay, and then you take the square root. So what does this end up being? You're laughing. What?
I forgot to square it on the
Okay,
page, so
yeah.
it's like, that's a big box.
Yeah, it is. Yeah, and so it ends up being 1 times 10 to the 1 times 10 to the minus 18 meters squared. You take the square root and you get 1 times 10 to the minus 9 meters, or 1 nanometer. Okay. Let's see. Yeah, you can still see it. Or 10 angstroms. Okay. That's not so bad, but I wanted to not blindside you on the test. Something similar to this on the test. The electrostatic potential, and then vocabulary. Knowing what's on that homework. Okay. Have some confidence. Okay, you guys can do this.